Good morning, afternoon, everyone. Thank you for being here today. I am excited to introduce our research on multi-batch nuclear norm adversarial network, MBAN, a novel approach for unsupervised domain adaptation, UDA. Background. In real-world computer vision applications, data distributions often shift across domains, posing significant challenges. Some examples include medical image analysis. Different hospitals use different imaging devices, causing domain shifts. Remote sensing image. Data from different satellites and time periods may vary significantly. If we directly apply a model trained on the source domain to the target domain, performance drops dramatically. This is because traditional deep learning methods rely on the independent and identically distributed IID assumption, which does not hold in domain adaptation scenarios. Domain adaptation, DA, is an important subfield of transfer learning, where the goal is to transfer knowledge from a labeled source domain to an unlabeled target domain. Many existing approaches rely on adversarial learning. Recently, DALN reuses the classifier as a discriminator. Although DALN has achieved significant performance improvement, the limited size of mini-batch often contains a small number of categories, resulting in the difficulty on calculating nuclear norm. To address these issues, we propose multi-batch nuclear norm adversarial network, MBAN, which performs more stable adversarial learning over multiple mini-batches, significantly enhancing domain adaptation performance. Our proposed method, MBAN, enhances feature transferability and discriminability through three key techniques: feature queue, probability, rescaling multi-batch nuclear norm discrepancy, MND. By the end of this talk, I hope to provide deeper insights into how to improve domain adaptation effectiveness. The schematic of MBAN, as shown in Figure 2. To avoid the tedious iterative updates, we use a gradient reversal layer for adversarial training in one-step backpropagation. Methodology. Our MBAN framework consists of three key components. 1. Feature queue traditional adversarial learning methods only use the current mini-batch for domain alignment, leading to unstable training. MBAN introduces a feature queue that stores features from multiple mini-batches, ensuring more stable and effective adversarial training by incorporating historical information. 2. Probability rescaling. In the target domain, the model may become overconfident in certain predictions, leading to error propagation. We introduce temperature scaling, which smooths probability distributions and prevents the model from making excessively confident yet incorrect predictions. 3. Multi-batch nuclear norm discrepancy, MND. Traditional adversarial learning computes domain discrepancies using a single mini-batch, which is highly sensitive to noise. MBAN computes the nuclear norm discrepancy across multiple mini-batches, performing a more global domain alignment and improving generalization. Our overall objective function is MBAN loss to CLS loss beta, MND loss where CLS loss, the classification loss in the source domain to ensure correct predictions. MND loss, the nuclear norm-based domain alignment loss. Beta, a hyperparameter balancing classification and domain alignment. Additionally, we adopt a min-max optimization strategy to stabilize adversarial learning. Theoretical insights. From a theoretical perspective, our method reduces the expected error in the target domain, where epsilon t h, error in the target domain, epsilon s h, error in the source domain, IW, 1 PQ. Domain discrepancy between source and target distributions, ETA. The error bound of the ideal hypothesis. By optimizing MND, we effectively reduce domain discrepancy, thereby lowering the target domain error and improving adaptation performance. Experimental results. We conduct experiments on several benchmark datasets, including Office 31, VISE DA 2017 Office Home. The results show that MBAN outperforms state-of-the-art SOTA methods such as DAN and DALN across all datasets. In our ablation study, we can clearly see that MBAN is superior to MBAN, W output, confirming the importance and effectiveness of caching features. Confusion matrices indicate that MBAN achieves higher classification accuracy in the target domain. DALN only calculates the nuclear norm on the current mini-batch. Due to the lack of enough category information in mini-batch, here exist numerous samples are misclassified, e.g., most samples of letter tray are misclassified as trash can. Feature visualization shows that MBAN learns more separable feature representations. We evaluated the prediction determinacy. DALN significantly improves the rate of correctly prediction of samples within the high probability, showing the effectiveness of the proposed method for improving determinacy. We conducted the sensitivity of Q-length C on Office 31. MBAN achieves the best performance when C equals 3. When C equals 1, the feature Q is difficult to contain enough category information for calculating MND. In contrast, when C equals 4, the Q contains more inconsistent features, which hinders domain adaptation. Conclusion: MBAN introduces feature Q, probability rescaling, and MND to enhance domain alignment. Experiments show that MBAN outperforms existing methods and achieves superior performance across multiple datasets. Future work will focus on scaling the model, integrating transformer-based architectures, and expanding to new applications. Thank you all for your attention. If you are interested in our work, feel free to check out our GitHub repository. I am happy to take any questions. Thank you.